Swayam Prabha. Digital India. Educated India.
How we can switch bases? Let us see. So, what do we do now? We have come up to now, what do we do? See, we have done whatever we could with functions. So, now it makes sense. After all, what are we trying to do? Switch bases and do what? We want to switch bases and go from one set of transformation matrices to another set of transformation matrices. That is what we want to do. So, it makes sense now to invoke our old friend, the transformation operator, right. Remember transformation operator? ORFI is equal to ORFI x1 dash x2 dash x3 dash equal to FI x1 x2 x3, but that is not what is going to be very useful for us at the moment. What is going to be useful is the relationship between OR and the transformation matrix. What is the relationship between OR and the transformation matrix elements? That is something that you need to remember. ORFI equal to k equal to 1 to n dki superscript f of R fk. For now, neglect this superscript f. If I do not write that superscript f, does that ring a bell? Have you encountered expressions like this earlier? ORFI equal to sum over k equal to 1 to n dki R fk. Remember, that is what we were saying a little while ago, is not it? Sum over k dki means once again we are going down. Why are we going down? Because d of R, what is d of R? It is a transformation matrix corresponding to the symmetry operation R, that d of R has been worked out using the coordinates, and now what we are doing is transformation of bases. That is why we take the transpose. I think this is something that you know. Why have I written F here? To denote that this transformation matrix that we are talking about is associated with the functions f functions and not g functions. Right now we are dealing with f functions, g functions, right. So, we have to label the transformation matrices as well. Matrices are actually going to depend on which basis you work with. So, you must label them f or g. Okay. Now, similarly, I can write the expression for the transformation matrix that works on the g functions. That will be OR Gj equal to sum over L equal to 1 to n dLj, then superscript g of R gl. Make sense? It is very important that we write the superscripts f and g here, because all we are trying to do at the moment is that we are trying to see how you can transform the the DGRs to DFRs or vice versa. When I say switching of bases, that is what I mean. When I change the base from F to G, then the matrices should also change from DFR to DGR for the same R. How to do that? That is the whole purpose of this exercise. To simplify this problem, I can simply, not simply, I can substitute Gj in OR Gj by the expression that we know, right. If I do that, what will the left hand side become? OR This is what it will become. We are only working with the left hand side, not the right hand side at the moment. We will come back to the right hand side later. You are experts in simplifications like these, right. We are now working only with the left hand side. So, it becomes OR operating on sum over I from I equal to 1 to n Bij Fi. How can I simplify this expression? Summation can come out. Why can the summation come out? Put it in a different way. It's linear. OR is a linear operator, right. So, when it operates on something, some number multiplied by a function, then the result is that number multiplied by OR operating on the function. This is what it is. OR is a linear operator. So, I can write it as sum over I equal to 1 to n Bij OR Fi. Are you okay? Fine. What is the definition of a linear function? If, what did we write there? If G equal to A into F, where G and F are functions, A is a scalar quantity, then ORG, that is OR operating on A into F, is equal to A multiplied by OR F. Alright. So, can I write this? Because it is linear? Fine. Are we all okay? Now, what will be the next step? I have OR Fi. Do I have OR Fi somewhere else? Right. So, I can substitute this. If I put it in, what do I get? Sum over I equal to 1 to n Bij, then sum over k equal to 1 to n d dki f of r fk. Put it. Alright, what more can I do? Do I know the expression of fk? Is it there somewhere on the slide? Huh? This? So, I can substitute for fk. I can write sum over L ALK GL. Done? Okay. So, now I have a little scary looking thing, but it is not all that difficult. Because after all, see what is there? This Bij, dki, ALK, these are all numbers, isn't it? What is the only function that is there in that somewhat scary expression? GL, right? So, this is what it should be, right? Sum over L equal to 1 to n something multiplied by GL. Okay. And see, there is the same functional form like the right hand side. So, you are almost there, isn't it? We are simplifying the left hand side and we are getting something that is of the same form as the right hand side. What is there inside the bracket? This order of summation does not matter, right? Where do you have two summations over I? L. One is L, the other is I. I can read it from here, maybe from a distance it might be a little blurred. You cannot sum twice over I. It is either a spelling mistake or something like that. Here there is, it is I and L. Okay. Now see, so what is equal to what? Now if I compare the right hand sides, this expression is equal to this expression E. I was wondering why Mehak is frowning. all right now? Huh? No? Where is what in between? That I is a spelling mistake, yes. I could not see it because the background was too bright perhaps. Please neglect that I, that is not right. Now see, what is this? This is ALK DKI BIJ, and what is there on the other side? DLJ. Remember the rule of matrix multiplication, right? These coefficients seem to be cutting off, cancelling each other. So if this is the case, when DLJ is equal to ALK DKI BIJ, then what does it mean? That means this D is a product of, well sorry, DG is a product of A, DF and B. So I can now go from matrix elements to matrices. Isn't that the rule of multiplication of matrices? So I can write this. Oops. Okay, in any case, you don't need those anymore. This is not too bright, I hope. So DG of R is equal to A DF of R B. So see, we have already got a relationship between the transformation matrices corresponding to the same symmetry operation R, but for two different bases, one the F functions, the other is G functions, right. And when will this hold? When can we do this? When we can express the F's as a linear combination of G's and the other way around. Is that always the case for linearly independent operators? Linearly independent operators, you should be able to do that. Okay. Now, but let us finish this story first. There is no point in keeping B as B, because we know very well that B is A inverse. Remember? And now I see the smiles, because the moment I replace B by A inverse, then I have something nice. I have something familiar, and that is a similarity transformation. So now see what similarity transformation does. A similarity transformation essentially switches the basis. That is why it is so important. It is not just some idle exercise that we were doing. A similarity transformation takes you from one set of linearly independent vectors as the base to another set of linearly independent functions as the base, right. So that is the power of similarity transformation. Okay, that is what transformations usually do. Have you heard of some more other celebrated transformation? What is the transformation everybody has heard about, at least every chemist has heard about, no matter whether you know the meaning or not? Fourier transformation, right. Nobody has IR NMR anymore, they say FTIR FTNMR, right. What is Fourier transformation? What does Fourier transformation do? Yeah, it takes you from time to frequency domain and vice versa. Please note domain. It takes you from time domain to frequency domain. Here also we are going from G domain to F domain or the other way around. Okay, that is what the similarity transformation does. It switches the basis. Right. So now to conclude this part of the story, I hope we have understood that transformation matrices for two linearly independent bases are conjugate to each other. We have just seen that DG and DF are conjugate to each other, not for any R, both have to be for the same symmetry operation. You cannot have C3 on one side and sigma V on the other side. Secondly, you cannot just use any matrix, right. You take any matrix under the sun and perform a similarity transformation, will you go from one base to another? You won't. What is the matrix that you have to use? What is the matrix that you used? You used A and B. What are A and B? They are the matrices that relate the bases linearly. Well, they are conjugates actually, but that is something that we can live with, I hope, right. Third is, this is something that I like you to work out yourself. Change of basis does not affect the multiplication rules. This is what I mean. I think this is something that is very simple, you can work it out. Can you work this out yourself? Not here, later. It is very simple, right. So now to conclude, what we have done after all this exercise is that we have arrived at this very important concept of equivalent representations. Equivalent representations. But the take home message from this part, and which is going to be pretty much the part for today, is two representations of a point group are equivalent if, the next word is very important, if for each and every symmetry operation R, you can write a similarity transformation using the same pair of matrices A and A inverse. And you already know that A and A inverse are not some arbitrary matrices. These are the matrices that correlate the f functions and g functions. Okay. So far so good. So what have we learned so far? We have learned the concept of equivalent representations. So this is very important. They are equivalent when you take one set of transformation matrices and then you perform similarity transformation using the same pair of A matrices. So think of C3V. What are the matrices? DE, DC3, DC3 square, D sigma V 1, D sigma V2, D sigma V3. Now you have to do the similarity transformation of each of these matrices using the same A inverse. Okay. Then what you get, if you get, is another set of matrices, then the representation that you generate that way is equivalent to the representation that you started with. Alright. This is the definition of equivalent representations. I want to give you a homework problem. I would love to work this out myself, but in any case we are running so much behind schedule. So please work this out, and my request is work this out this evening. We are talking about a lot of abstract terms, right? We are chemists, we are not mathematicians. So we only believe something when we can work it out on something that is more tangible, right? So this is the problem. So consider two sets of p orbitals, px, py, pz, and p plus 1, p minus 1, p0. Okay. How they are related is given in Atkins physical chemistry book. Not exactly page 337 maybe, but you have to start from 1 or 2 pages earlier. 337 is the final result. Okay. You see how they are related. Now what I would like you to do is you work out the transformation matrices for both the sets for all the symmetry elements of point group C3V. So how many matrices do you generate? E, C3, C3 square. E is very easy. Okay, I won't even count E. C3, C3 square, sigma V1, sigma V2, sigma V3. 5 into 2, 10, plus the 2 bonus matrices E. Okay. Then what will be the next step? In the first step, what have you done? Okay. Next step is this: with the help of the matrices that correlate Px, Y, Pz with P plus 1, P minus 1, P0, prove the equivalence of the two representations thus generated.